Alright, so for our next problem, we're going to be looking at a turbine, and we're going to draw a turbine like that. So this turbine is inside some sort of fluid, so there's a couple of specific areas that we're going to want to look at. So the first is this area right around the turbine. This is like what's directly being acted on at the turbine. And then we're also going to want to consider an area of fluid that is going into the wind turbine and an area of fluid coming out of the wind turbine. So this is going to be point 1, this is going to be point 2. Alright, so at this point in the middle, well, across all of the points, the fluid's going to be the same, so our density is going to remain constant for all 3 points. But the velocity of this fluid is going to be changing. So at point 1, we're going to have a velocity of 1. Point 2, we're going to have a velocity of 2. And in the middle here, we're just going to have a velocity of v. So we know that the velocity at 2 is going to be less than the velocity at 1 because this turbine is going to take out the majority of the kinetic energy of the wind, and so it will lose speed. And since this velocity change, we also know that this area is going to change of the area that we're going to look at. So we're going to use A for that over here, and then A1 here and A2 here. Alright, because then this ratio of velocity to air is going to remain constant. So throughout the problem. So we're going to be looking at this in terms of a momentum energy balance and a kinetic energy balance, or just a momentum balance and an energy balance, kinetic energy balance. So we're going to start with the momentum balance. So for the momentum balance, we have that the change in momentum, which momentum is the mass times the velocity of our system, for the change in time is equal to the mass flow rate going in times the velocity going in minus the mass flow rate going out times velocity going out minus plus the force that is acted upon it. So from here we're going to say that our system is at steady state, and therefore any derivatives with respect to time go to 0. We're also going to consider our mass going in. So this mass of fluid that we're looking at every point is going to be the same. We're going to look at the same mass of fluid, and that's why this will remain constant for each. So it's so this will remain proportional, I guess, not constant, proportional throughout. So because of that, we can look at, we know that our mass in, so our mass rate in is equal to our mass rate out, and that is going to be equal to our rho VA. So at this point we can rearrange this equation a little bit. So we've got 0 on this side, we're going to subtract the force over here, and we're going to have that rho VA times velocity in, which is V1, minus V2, which is our velocity out. So this is our momentum balance equation, and now we are going to look at, oh wait, we're not quite done here. So we want to look at the power that is generated by this wind turbine, so we need to introduce power into this equation. So we know that power is equal to the force times the velocity, we're going to have negative force times velocity. So then we can plug that in here, so we just need to multiply this by velocity. So we got rho times velocity squared times area times v1 minus v2. This is the equation we're going to compare. So now we want to look at our kinetic energy. So again, in terms of power. So the power of our kinetic energy, or our power is going to be our change in kinetic energy per mass times the mass flow rate. So at this point, we know that kinetic energy is 1/2 mv squared. So plug that into this. So delta kinetic energy, so we need to change the kinetic energy at 1 minus kinetic energy at 2. So that will end up being, and the mass is going to cancel because 1/2 mv squared, mass cancels. 1/2 can be pulled out of this subtraction. So we have that it's 1/2, and then we just have velocity at 1 squared minus velocity at 2 squared. And then times this mass flow rate. So we just determined earlier that the mass flow rate is rho VA, so we'll keep that. Right. So then from here we have two equations for power, so we're gonna set those equal to each other and solve for the velocity in the wind turbine. Alright, so we have that the velocity at 1 squared minus the velocity at 2 squared over 2 times rho VA is equal to rho V squared A times V1 minus V2. Alright, so rho cancels, one of these velocity cancels, A cancels. So then we're left with this term, 2 velocity, and then this. And I'll notice this is factored into here, so I'm going to factor this out right now. So we're going to have V1 minus V2 times V1 plus V2. So it's just the factored form of V1 squared minus V2 squared. So over 2 is over 2 times V1 minus V2, because we'll divide that across, and then that is equal to our velocity. So you can see this cancels, and we've got that our velocity is equal to V1 plus V2 over 2. And you'll notice that this is actually just the average of our velocity coming in with our velocity coming out. So that's what we have here. And then, so what we can do is we can plug this back into one of our two equations. So we can either choose this one or this one. We'll get to the same place, but I'm just going to choose this one because I can just put it right there. And I'm going to change colors to make it more clear. So I'm going to plug this velocity back into this equation. So we're going to have that power is equal to V1 squared minus V2 squared over 2 times rho times A times V1 plus V2 over 2. Alright, so then we can combine some terms. We've got that power is equal to rho times A over 4. We combine these twos, and then times, so then we're going to combine this and this. So that's V1 cubed minus V1 and V2 squared plus V2 times V1 squared minus V2 cubed. Alright, so at this point we can create a new variable, and we're going to create a variable for the ratio of our two velocities. So So we're going to do that over here. We're going to call this variable r for ratio. It's just going to be the ratio of v2 to v1. And we're going to try to incorporate this into here. So first what we need to do is get all of these terms into sort of the v2 over v1. So we'll divide everything by v1 cubed. Because that'll bring this term down to 1, and then this one term will have a v1 in the bottom, and along with all of the others. So we have our pressure is equal to rho times the area over 4. So divided by v cubed, or v1 cubed is 1 minus. So it's v2 squared. So divided by v cubed 3, one of these cancels, we get v1 squared. That's v2. So v1 squared divided by v1 cubed is v1. And then minus v2 cubed over v1 cubed. Alright, so this works out really nicely. And we have that the pressure equal to rho times the area over 4 times 1 minus r squared plus r minus r cubed. Alright, so then at this point we want, it makes sense that if we had a turbine, we would want to know what is the maximum power that we could get out of this. And so to get at a maximum power, that means that the derivative of the power is going to be equal to 0, because we're looking for maximum, so derivative is equal to 0. So we're going to set this derivative, take the derivative of this and set it equal to 0. So it's going to be the derivative with respect to r. So I have that dp dr is equal to, so this rho a over 4 is a constant, rho a over 4. Alright, so times so this term disappears, and we've got negative 2r plus 1 minus 3r squared. Alright, so then set it equal to 0. So from this point, take it up here. This term right here is constant, so it divides out, and we're left with just this. So we've got negative 3r squared minus 2r plus 1 equal to 0, and then we can factor this out. So we've got 3r minus 1 times negative r minus 1 equal to 0. So from this point, we take each of the factors and set them individually equal to 0. So we've got 3r minus 1 equals 0, r equals 1/3, and then we've got negative r minus 1 equals to 0, r equals to negative 1. Alright, so when we look at these two and remember what r means, so r is velocity at 2 over the velocity at 1. And we know that the velocity at 2 needs to be lower than the velocity at 1. And this r equals negative 1 just really doesn't make sense. Our velocity is not going to be negative, or else we'd have, air going in and then turning around and going back out, which is not really how turbines work. And so this one does not make any sense. However, r is equal to 1/3 does make a lot of sense, and we can confirm that indeed the velocity at 2 is less than the velocity at 1. So this is the ideal velocity ratio that we want to have if we want to get the maximum power out of our turbine.